Hello and welcome back to part 2 of this video series about electromagnetic interference in relation to multicopters. My main goal is to answer the question, is electromagnetic interference made up or is it something real that can cause serious problems? In part 1, I explained how one wire can induce an electromotive force, or abbreviated EMF, into another wire, causing a voltage difference in that wire. If you haven't seen this video, I strongly recommend that you watch this video first. You can find the link to this video in the description. In this video, I will conduct some experiments to visualize the amount of energy that is induced by the EMF. During the last experiment in part 1, it became clear that the changing magnetic field around the battery wires can easily induce a 300 mV peak-to-peak EMF in a 20 cm or 7.5 inch wire. The electromotive force, or EMF, is measured in volts and can be calculated with the Faraday-Lenz law, as I explained in part 1. If the electromotive force is induced in a closed-loop circuit, a current will flow through the circuit. For example, in a wire, a 300 mV EMF is induced by a changing magnetic field. The total resistance of the circuit is 1 ohm. By applying Ohm's law, we can now calculate that the current in this circuit will be 0.3 amps or 300 milliamps. Now it's very important to understand that the EMF is induced in the wire. This makes the EMF completely independent from the attached load. You can compare this wire with a battery that has a very low internal resistance. Depending on the consistency of the magnetic field, this wire can deliver a significant amount of power. To visualize this, I will conduct another experiment. Here you can see a 13-turn coil placed on top of the battery wires. The only reason I use the coil is to boost the voltage so I can light the LEDs. When the motor is running, the induced EMF in the coil causes the LEDs to emit light. Despite the fact that there are 13 100 ohm resistors in parallel with the two LEDs. Now watch what happens when we remove all the resistors from the breadboard. Now you might think by judging the brightness of the LEDs that the voltage increased significantly. But watch what happens when I connect the breadboard to a bench power supply. Now it's a little hard to see, but it takes approximately 1.68 volts to light the LEDs the same as they did when powered by the EMF. The current at this moment is 300 milliamps. To get the same brightness as with the removed resistors, I only have to increase the voltage to 1.75 volts. So when I removed the resistors during the test, the voltage only increased 4%. The current, on the other hand, decreased with 300 milliamps. To confirm this, I also ran this test with an attached oscilloscope, giving me the exact same results. Before we continue, it's best to summarize these results. The electromotive force, or EMF, is measured in volts and is induced in the wire. An EMF induced in a wire is like a battery with a very low internal resistance. The EMF voltage remains the same regardless of the load. The power that the EMF can produce depends on the consistency of the magnetic field. In normal situations, Ohm's law is used to calculate the current in a circuit. And now we finally have enough basic knowledge and understanding to try some real-life examples. Here I have a MPU 6050 gyro that is connected to a Arduino. As you can see, the wires from the Arduino to the gyro run in close proximity of the battery wires. The oscilloscope is set to AC. This means that the 5-volt DC part is removed and only the voltage change, or noise, is visible on the screen. The sensitivity is set to 100 millivolts per division, and I will measure the 5-volt input voltage to the gyro breakout board. When the motor is running, the changing magnetic field around the battery wires induce an EMF in the wires to the gyro. This EMF creates a voltage difference, or noise, of almost 400 millivolts peak to peak. This noise is superimposed, or added, onto the 5-volt gyro supply voltage. Now the MPU 6050 gyro itself runs on 3.3 volts. So there's a voltage regulator on the PCB. The question is, will the noise on the input of the voltage regulator transfer to the output of the voltage regulator? And as you can see here, when I measure the noise on the 3.3 volt output of the voltage regulator, we don't see anything that even looks close to the noise that we saw on the 5-volt input. So what is going on here? To find out what is exactly going on, we need to take a look at the datasheet of the voltage regulator. Let's take this MIC 5205 for example. In the datasheet, we can find detailed information about the power supply rejection ratio, or abbreviated PSRR. This is the amount of noise that the voltage regulators can reject and is given in dBs. As you can see in this graph, the PSRR is frequency depending. A short glimpse on the oscilloscope tells us that the frequency of the noise is approximately 83 kHz. For this frequency, the datasheet of the MIC 5205 returns a PSRR of approximately -40 dB. With this formula, it is possible to calculate the output noise of the voltage regulator when 1 volt of noise is applied to the input of the voltage regulator. So for every volt of noise, the output only changes 10 millivolts. If we apply this to the measured 400 millivolts on the input of the voltage regulator, the noise on the 3.3 volt output will only be 4 millivolts. Please note that not all voltage regulators have the same power supply rejection ratio. But for now, let's say that a voltage regulator is an excellent noise filter. But what happens if the gyro is connected to a 3.3 volt microcontroller like the Arduino G or the Arduino Zero? Then the voltage regulator cannot filter the noise because it has no voltage difference to work with. In this case, the noise that is induced in the wires is directly passed through to the gyro, as I will show you in this example. I connected the gyro to the 3.3 volt output of the Arduino Uno and connected the scope to the 3.3 volt output of the voltage regulator. As you can see on the screen of the scope, the capacitor is unable to reduce the high power noise. This amount of noise will have a negative effect on the gyro's performance and can cause quadcopter instability. But what about the other two wires? The data and clock signals from the I2C bus. These wires are also affected by the induced EMF. Now here you can see the clock pulse of the I2C bus. Now look what happens when I start the motor. The induced EMF causes the 0 volt level to jump up and down for almost 500 millivolts. To have a better understanding of the problems that might occur, we need to have a look at the datasheet. In the datasheet of the MPU 6050, we can find the voltage levels that represents a digital 0 or 1. For example, a voltage lower than the supply voltage times 0.3 will always be 0. Everything above is undefined territory. So 3.3 volts times 0.3 is 0.99 volts. If the jump in voltage is large enough, it can cause a premature clock pulse. The gyro's response may cause the main program to hang if there is no adequate software error handling. And in most situations, this is not the case. Okay, by now I think you have seen enough examples to get a good understanding of electromagnetic interference caused by electromagnetic induction. In the next and last video of this video series, I will conduct some final examples, talk about shielding and highlight the important parts. I will add a link to this video in the description. Thank you for watching and give this video a thumbs up if you learned something.